Good morning, students. Today we will be discussing about carbon and its compounds. Well, indeed, we are talking about one of the most important non-metal, carbon, and in fact the most versatile element in nature, carbon. Carbon having symbol C with its atomic number 6, mass 12. Well, we also have one more isotope of carbon, commonly referred as C14, which we will discuss later, it being a radioactive thing. Now this carbon 12, if we go for its configuration, electronic configuration, that is 2, 4, in its K shell we are having 2 electrons, and in L shell we are having 4 electrons. So we see here clearly that carbon is having 4 electrons in its outermost shell. So we say valency of carbon is 4. So it is tetravalent. Well, when I talk about the versatile nature of carbon, I am talking about the presence of carbon in nature and how and where it exists. Definitely, we are talking about carbon and its compounds, so we are talking about organic chemistry. In organic chemistry, we discuss carbon and its compounds, carbon and its derivatives. Well, the word organic, when we see to this word, we had a general myth that all organic compounds, they cannot be synthesized within the laboratory, but require some natural vital force which is prevalent, which exists within the living organisms for its creation, for its synthesis. It was Berzelius who gave a theory by the name of vital force theory. Berzelius, in his vital force theory, said that for the creation, for the synthesis of these organic compounds, we require some mysterious, unseen, natural forces which are prevalent, which are existent within the body of a living organism. Then only it can create, synthesize these organic compounds. But this vital force theory, it received a big blow when Wöhler came up with a new concept that these organic compounds can be synthesized outside in laboratories as well, outside living organisms. What he did, he took ammonium cyanate and he heated it. And when he heated this ammonium cyanate, there was a sort of rearrangement and it formed urea. Now you see here, this ammonium cyanate is inorganic compound. And urea, on the other hand, is organic. This conversion of this inorganic compound, ammonium cyanate, on heating, which results due to the rearrangement of these atoms within the compound, results in the formation of urea, which is an organic compound. This thing came to be known as Wöhler synthesis. And this was the beginning of the era when these organic compounds started to be formed in laboratories. Now the people, the scientists, they started synthesizing many organic compounds within these laboratories. And this myth of this vital force theory that the special force is required for the creation of these, for the synthesis of these organic compounds within the living organism, it broke because of this Wöhler synthesis. After this, we'll switch back to the versatile nature of carbon. In today's world, if we analyze, carbon is found everywhere. It will be not wrong to mention here that It's also referred as, carbon is referred as element of life. In fact, every living organism contains carbon. Well, indeed, if you have to mark or show the presence of carbon in the living organism, you take any carbon compound, take any substance or any living form of substance, you just burn it. It will produce a gas, carbon dioxide. This carbon dioxide gas can be passed through lime water, and we know when this carbon dioxide gas is passed through lime water, it turns lime water milky. Well, the question arises again about the versatile nature of the carbon. We are studying here organic chemistry, and we know whole of chemistry is divided into basic three parts. We have physical chemistry, we have the inorganic chemistry, and then we have organic chemistry. Well, you must be thinking that if we are studying organic chemistry, which means the chemistry of carbon, in whole of the periodic table where we are having almost more than 118 elements now, why we had chosen this carbon and assigned a special branch of chemistry to this carbon, organic chemistry? There must be some reason behind that why we had given a special status to carbon. And the answer is that carbon forms a large number of compounds. It forms large number of compounds which no other element in whole of the periodic table can form. Well, to form compounds, it mostly collaborates with hydrogen, oxygen, nitrogen, and we have a huge number of hundreds and thousands of these carbon compounds available. Now again the question arises, what makes carbon versatile? What special is carbon having that it is able to form such a large number of, such a huge number of organic compounds? There must be certain special characteristics, certain special properties associated with carbon which enables it to form these large number of compounds, and well, we will be discussing all of them right here. So, coming back, we will be discussing about the versatile nature of carbon, the reasons why carbon is able to form such large number of compounds. So, we're discussing about the reasons why carbon forms large number of compounds, which depicts its what? Versatile nature. Well, there are many reasons, and we'll be starting with the first, which is tetravalency of carbon. As already discussed, that carbon is having 4 electrons in its outermost shell, so it will be requiring 4 hydrogens to complete its octet. Likewise, in methane, we have CH4, so 4 hydrogens come and they share the electrons with carbon, completing its octet and the duplet for hydrogens, resulting in the formation of the most basic hydrocarbon, the first member of hydrocarbon, methane. Well, we see here, valency simply means the combining capacity of an element, and here we see carbon combines with maximum of 4 hydrogens, so it's able to form 4 bonds with 4 hydrogen atoms, resulting in valency of 4. So we use the word tetravalency or tetravalent for carbon. Now carbon is having this liberty. It can be combining with the elements who are having valency 1, 2, 3, and 4 even. So this enables carbon, because of its tetravalent nature, to form a large number of compounds. So this was perhaps the first reason. The second reason is catenation. Now when we talk about catenation, catenation simply means the property of self-linkage. Property of self-linkage in which these carbon atoms, they combine within themselves to form large chains. You can see here, no other element is having this property, this unique property like carbon, so that it can combine with itself to form such a large number of chain. Now, indeed, there are some elements like sulfur, silicon, they also show the property of catenation. But in them, it's just the matter of few atoms. But in case of carbon, there are hundreds and thousands of atoms which combine to form these long chains. I will give you an example here. We have a CH2 double bond CH2. This is ethene. Now we all know ethene is basically the second member, the first member of this alkene family. They are unsaturated hydrocarbons because having this double bond thing in them. So this ethene, it undergoes what we call as polymerization. Now poly means many, merization means to get together, to bind together. So these n number of ethene units, they combine together, resulting in the formation of what we call as polyethene, against what whole world is struggling right now. So this is our polyethene. CH2, and as I said, n number of CH2 units. N number of CH2 units combine together to form a long chain of like CH2, 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 and this chain goes on. At least for a strand of polyethene to get formed, you require at least 20,000 ethene units. And these 20,000 ethene units, if they polymerize together, that means we have this chain which is in this polyethene comprises of, because every ethene unit is having 2 carbons, so this chain will be at least of 40,000 carbons in a strand of polyethene. So now you can imagine these carbon atoms, they can combine with themselves, they can bind with themselves, join with each other to form such a such a large chain. And this property is called as catenation. I will again repeat, catenation is the property of self-linkage in which carbon atoms combine with itself, carbon atoms join with itself to form long, long chains, resulting in the formation of a new and more number of compounds. Suppose if we start from methane, which is having just 1 carbon atom in it, then we can shift, if 1 more carbon gets added up, it will form ethane, then accordingly propane, butane, and the number goes on and on and on. So this was the second property of catenation, which results in a large number of compounds. Now the third property which enables carbon to form large number of compounds is its ability of carbon to form multiple bonds. when we say multiple bonds, it means carbon can form a carbon-carbon single bond. It can form a carbon-carbon double bond and a carbon-carbon triple bond. Well, a bond is formed when these carbon atoms, they share a pair of electrons within themselves or with other atoms. Likewise, we see here, in case of this, where we see a carbon-carbon single bond, carbon with this carbon is sharing a single pair of electrons. And here it will share two pairs of electrons. And in case of triple bond, we see it is sharing three pairs of electrons. Let me take an example here. For example, we are discussing the case of C2H6, which is ethane. Let me draw its structure. C carbon bound with another carbon, and then we have hydrogens completing its tetravalency. So we have CH3, and in this case, carbon and carbon are bound together with a single pair of electron, resulting in the formation of single bond because they are sharing one pair of electron. So this carbon and carbon are having single bond. But if we see this case here, in carbon-carbon double bond, we will take C2H4, which is ethene. Here it was ethane. Now this ethene, if we draw its structure, it is CHH. So it is CH2 double bonded with this carbon, CH2. Now you see here very clearly, here also carbon is sharing 1, 2, and 3 electrons, and this carbon is also sharing 1, 2, and 3 electrons. Now the fourth electron of this carbon, let me presume it's still free. And carbon, in order to complete its valency, tetravalency, needs more hydrogens. This carbon requires one hydrogen, and this carbon here requires one more hydrogen to complete its octet, to complete its tetravalent nature. Now, hydrogens are not available. But in that case, what this carbon has learned, it has learned the art of sharing this one more pair of electron within itself, resulting in the formation of double bond. And because of this double bond, a new compound is formed, which is ethene. And if we now look at this carbon-carbon triple bond thing, we have C2H2, which is ethyne, and in this case, carbon sharing a pair of electron. This is one hydrogen. This is one hydrogen. So they are having just two hydrogens, one with this carbon and one with this carbon, leaving two pairs of electrons of this carbon as such. Now again, because carbon is having the ability to form multiple bonds within itself, so carbon shares this and this pair of electron within itself, resulting in the formation of triple bond in this case. So we have this series of compounds in which we have carbon-carbon single bond. They are referred as alkanes. We have a series of compounds in which carbon-carbon have a double bond in between them. This is referred as alkenes. And then we have a series of compounds in which carbon-carbon have triple bond within them. We refer them as alkynes. So alkanes having carbon-carbon single bond, alkenes carbon-carbon double bond, and alkynes carbon-carbon triple bond. Well, this alkane class of compounds in which carbon compounds are having, or these hydrocarbons are having single bond between these carbon atoms are generally referred as saturated hydrocarbons. And these alkenes and alkynes having a double and a triple bond between them are referred as unsaturated hydrocarbons. Saturated hydrocarbons and unsaturated hydrocarbons. Well, we have to understand the concept of saturation. Saturated and unsaturated here with reference to, with context to carbon compounds, with context to hydrocarbons. Now, well, we are very aware with this, the term when it's used in case of solution, saturated solution, unsaturated solution, the saturated solution being the one in which no more solute can be added to that solution at that particular temperature. And unsaturated one is the in which more solute can be added at that temperature. So when it comes to level of understanding, saturated in which addition is not possible and unsaturated in which addition can be done. Addition is possible. Look at this alkyne here. We have a carbon-carbon triple bond. We have a carbon-carbon triple bond here. And what forces carbon to form this triple bond here is non-availability of these hydrogen atoms. We had just one hydrogen here and one hydrogen here. So this, just two hydrogens available for these two carbons. It forces this carbon, because hydrogens are not available, these carbons are forced to form multiple bond within themselves. Now, what in case if I supply this ethyne, supply this triple bond compound with hydrogen? What will happen then? Earlier, hydrogen was not available. They resulted in the formation of triple bond. Now I am supplying hydrogen to them. In fact, something needs to happen. Now, what will happen? One hydrogen will go to this carbon, the other hydrogen will go to this carbon. Now, resulting in the formation of, now see, this carbon is having just one with it. And when one more hydrogen gets added to it, similarly, this one more hydrogen gets added to this carbon, the triple bond, which was earlier here, will get reduced to now a double bond. So it will take the form of this. So what we was having earlier is ethyne. Now ethyne will be converted to ethene. So alkyne gets converted to what? Alkene. A triple bond compound gets converted to what? A double bond compound. Means in this ethyne, in this alkyne, in this triple bond compound, the addition of hydrogen was possible. What I told you earlier, when addition of solute is possible, we call it unsaturated. So this hydrocarbon is termed as unsaturated hydrocarbon because in this case of triple bond, the hydrogen gets added up. So we can add hydrogen in this case. So this addition of hydrogen shows that these alkynes, this ethyne, these alkynes, they undergo addition reactions. So they undergo addition reactions. Now we come to, from ethyne, we come to ethene. Ethyne, when hydrogen is added to it, it undergoes addition reaction, forms ethene. Now ethene is having a carbon-carbon double bond. Double bond means it is sharing two pairs of electrons in between two carbons. Now what I do here is, can I add again the hydrogen to it? If we see the possibility of this hydrogen getting added to it, we see one hydrogen will go to this carbon, the other one goes to this carbon. And earlier it was CH2, CH2. Now when these hydrogens get added up, this double bond gets vanished and it becomes CH3 and CH3, and you see it takes the form of ethane, or carbon-carbon single bond compound, which we see here. So it results from ethene, it now forms ethane, and it's clear evident that in this ethene, the hydrogenation was possible, the addition of hydrogen was possible, as it was possible in ethyne. So ethyne, we said hydrogenation, the addition of hydrogen was possible, it undergoes addition reaction. Similarly, in ethene, it also undergoes hydrogenation, addition of hydrogen, addition reaction. So as we term this as an unsaturated compound. Similarly, when addition of hydrogen is possible here also, it is also unsaturated hydrocarbon. So both ethene and ethane means both alkenes and alkynes, as already said, are unsaturated hydrocarbons. Now let's look at this case of ethane. Now I can see all the 4 electrons of carbon are engaged, 3 with the hydrogens and 1 within themselves. Same with this carbon. Suppose if I add more hydrogen, is there any vacancy for this hydrogen to get bound to these carbons? Well, we do not find any electrons here which would have been combined with this hydrogen, so the combination of this hydrogen towards this is not possible. That means this alkane, this ethane, will not undergo addition reaction. This ethane here will not undergo addition reaction. So addition reactions, we can term here, addition reactions are the characteristic feature of alkynes and alkenes. Addition reactions are the characteristic features of unsaturated hydrocarbons, that's alkenes and alkynes. But what for these saturated hydrocarbons? When I say no addition is possible, as in case of solutions, saturated solutions, you cannot add more solute. Same is the case here. You cannot add more hydrogen because valencies are already satisfied. So no addition is possible. So when there is no addition possible, we say this ethane or alkanes, they are saturated hydrocarbons. Well, if alkenes and alkynes, they undergo addition reaction, there must be something for these saturated hydrocarbons, that's alkanes, and that thing is substitution reaction. So we were talking about substitution reaction in case of alkynes. So if we have CH4 here and we add chlorine to it, and this reaction takes place in presence of sunlight, we see, suppose this is CH and we're adding chlorine to it. What happens here is this H and Cl, they combined here, resulting in the formation of HCl. And what we find here is left is this C with these 3 hydrogens attached to it, and the chlorine comes in place of this hydrogen, resulting in the formation of CH3Cl, which is chloromethane. Now, just analyze it. You see here the chlorine wants to take the place of hydrogen. But carbon, being tetravalent, is having its 4 electrons with these 4 hydrogens. Now, if there is no place, no room for chlorine. So if chlorine has to get in, this chlorine wants to get in, we have to remove something. So what happens? This H is being removed taken away by this chlorine, creating a vacancy for this chlorine to come in. So it is a clear case of substitution. Here, this chlorine substitutes this hydrogen, means comes at the place of hydrogen, and hydrogen moves away in the form of HCl with it. So what we hear here is that this hydrogen gets removed by this chlorine, gets substituted by this chlorine, and we have substitution reaction here. And this substitution reaction is the characteristic feature of alkanes. As we had addition reactions, they were the characteristic feature of alkenes and alkynes. Similarly, these alkanes, they do not undergo addition reactions, but they undergo substitution reactions here. So we are done with this saturated and unsaturated thing, along with this addition and reactions and substitution reactions. So I will summarize it. Till now, what we have discussed is about the reasons why carbon forms large number of compounds. The first reason that we gave was about tetravalency of carbon. The second reason which we talked about was catenation, the property of self-linkage. And the third reason was ability of carbon to form multiple bonds, to form single, double, and triple bonds, resulting in the formation of three classes, three series of compounds: alkenes, alkenes, and alkynes. And at the same time, we discussed the saturated and the unsaturated hydrocarbons. We discussed about the addition reaction and the substitution reaction as well. Now, the fourth reason for this carbon to form the large number of compounds is isomerism. Perhaps it is one of the most important area which needs to be discussed. Isomerism is the phenomenon in which two or more compounds have same molecular formulas but different structures. Now, two or more compounds having same molecular formula and different structures, such a phenomena is called isomerism, and the structurally different forms are called isomers. Let me give an example here. C4H10, we all know what it is. We say it is butane. Now, if we see this butane, and if I tell you to draw its structure, perhaps the first thing you will do is draw the straight chain of carbons, 4 carbons, and then you place the hydrogens as per their valencies. So this is the structure of this, and the formula is as it is, C4H10. So we call this thing as simply normal butane. Now, if someone among you comes with a structure like this, says, sir, I am using the same raw material of 4 carbons, and now I'm assigning these hydrogens to these carbons. Assigning these hydrogens to the carbons as per their valencies. And he comes up with a structure like this. It's again C4H10. So we can see the molecular formula in both these cases is same. We had C4H10. This is also C4H10. We call it isobutane. It is having the molecular formula same as that of butane, which is C4H10. But when we look at and compare the structures, this is a straight carbon chain structure in which carbons are linked, 4 carbons are linked in a straight chain. But in this case, we're having 3 carbons linked in a straight chain, and this middle carbon is attached to this carbon, means having a branch. So it's a branched hydrocarbon. Perhaps the formulas are same, the structures are different. So when we have such a case, such a phenomena, that 2 or more compounds, perhaps based on their structure, they are not same, they are different compounds. This is normal butane, N-butane, this is isobutane. If I give its IUPAC name, this is butane, and this becomes 2-methyl propane. So definitely it is a different compound. Both of them are different compounds, having same molecular formula, but different structures. Such a phenomena in which two compounds or more than two compounds have same molecular formula. They're having same molecular formula, but different structures is called isomerism. And these structurally different forms, which we are having here, N-butane and isobutane, they are called isomers. And likewise, we are having here, in case of butane, we are having 2 isomers. For pentane, we can have 3 isomers, and the number keeps on growing. And such phenomena results in the formation of large number of compounds for carbon. So in totality, we discussed about 4 reasons. The first is tetravalency, second is catenation, third is ability to form multiple bonds, fourth is isomerism. All these 4 reasons contribute for the formation, towards the formation of large number of compounds by carbon, resulting in its versatile nature. Dear students, now we will be discussing about the nature of bonding in carbon. Well, as already mentioned and discussed, that carbon is having 4 electrons in its outermost shell, and its valency being 4, so it's tetravalent. Well, if we look at the bonding pattern, carbon having 4 electrons in outermost shell means there arises 2 possibilities in which we can say that carbon can either lose 4 electrons, and after losing these 4 electrons, it can result in the formation of C4 positive ion. And it can also gain 4 electrons and can become C4 negative ion. Now, gaining 4 electrons and losing 4 electrons, is it possible? Let's discuss why is it like this carbon cannot form C4 positive or C4 negative, either if it loses 4 electrons or gains 4 electrons. Let's see, in this case where we presume that carbon will lose 4 electrons. But will it lose 4 electrons of its own, or we require some energy for these electrons to be lost by this carbon? Well, the energy which is required is ionization energy. At every step, when carbon will start losing electron, it has to lose 4. Suppose it loses the first electron, then the second electron, then the third electron, and the 4th electron. At every step, when it starts losing these electrons, it requires energy. We have to supply this ionization energy to this carbon to make it lose its electrons. But is it really possible for us to supply such a huge amount of energy? Well, see, if we see for the first electron, let's presume we supply that much of energy to this carbon and it loses 1 electron. But after losing 1 electron, the carbon will form C1 positive ion. Now, the second electron which we have to take out, which the carbon has to lose, we have to extract this electron from the C1 positive ion. And because we are extracting a negative particle, electron, negatively charged electron, from a positive ion, so we have to supply in more energy. So for second electron, the value of ionization energy, second ionization will be much, much higher. Similarly, if suppose we are able to do that, then the third electron needs to be extracted from C2 positive ion. And then there we have to supply a even bigger amount of, larger amount of energy, which perhaps for us becomes very difficult. And then suppose the third electron and the fourth electron from a C2 positive, 3 positive ion. So practically supplying that much of energy to this carbon is not possible. So carbon does not prefer to lose 4 electrons, and the simple explanation to it is due to energy considerations. So due to energy considerations, carbon will not be able to lose its 4 electrons. So it cannot form C4 positive ion. Now we come down to how if it gains 4 electrons. Let's presume that carbon will start gaining 4 electrons in the same way, the first, second, third, and the fourth electron. See, every time any atom of any element gains an electron, it has to lose energy on gaining an electron. And that energy which it loses on gaining electron is called electron gain enthalpy. Electron gain enthalpy. Earlier it used to be also called as electron affinity, but the proper term is electron gain enthalpy. It is the amount of energy which is released when an atom accepts an electron to become an electronegative ion. So if it gains the first electron, it has to lose some energy. Then again it will gain the second electron, it loses energy, third, fourth. It has to keep on repeatedly losing energy. Again, due to energy considerations, it's not possible for carbon to lose such a huge amount of energy. So, due to energy considerations, this is not possible. And one more reason. Suppose we say carbon gains 4 electrons. Now, see, the atomic number of carbon is 6. That means in its nucleus, there will be 6 protons. There will be 6 protons. And for these 6 protons, it is very difficult to hold on to 6 plus the gained 4, that is 10 electrons. Now, 10 electrons held by this small nucleus of carbon, it will be very difficult, impossible for it to hold on to 10 electrons. So, again, formation of this C4 negative ion is not possible. So, if you have to answer that why carbon cannot form C4 positive or C4 negative ion, there is a one-line answer for it because of, due to energy considerations. Here we have to give in energy. Here carbon has to release energy. So due to energy considerations, it's not possible for carbon to form such a large number of compounds. So this possibility of forming C4 positive, C4 negative ion, it ends here. Then if carbon is not able to form C4 positive or C4 negative ions, then what carbon is able to do? How it will satisfy its thirst, how it will satisfy its want, how it will satisfy its valency. Well, carbon has learned one more art, that is, it is having 4 electrons in its outermost shell. So what carbon does, it, as I had already mentioned it earlier in case of tetravalency, it shares its electrons with other elements. Suppose this is hydrogen. Hydrogen comes with its 1 electron, and this carbon shares its electrons with these hydrogen, completes its octet. But here it does not lose, it does not gain. There is a mutual sharing. And this mutual sharing of electrons, the sharing of electrons results in the formation of what we call as covalent bond. So carbon prefers to share its electrons with other atoms of other elements, resulting in the formation of covalent bond. Now, suppose in this case of methane, carbon shares 4 pairs of electrons. So we say, in terms of its how many pairs of electrons or how many electrons it shares, we express it in terms of its covalency. So its covalency is here, again, 4. This was about the nature of bonding in carbon, how it does not form ionic bonds, but it results in the formation of covalent bond by sharing of its electrons. Dear students, now we will be discussing about the next topic, that is properties of carbon compounds, and let's start with the first property, that is combustion. Now, combustion simply means the word it means to combine with oxygen. And when I here talk about oxygen, I mean to say I'm talking about molecular oxygen. Molecular oxygen, which is in the form of O2. Now, combustion simply means the act or the process of heating, strongly heating carbon compound or any carbon-related substance in air. Likewise, if we strongly heat carbon in presence of oxygen, we know it burns. So combustion, we can also say it's a process of burning. Now this carbon combines with oxygen, resulting in the formation of carbon dioxide and releasing large amount of energy in the form of heat and light. Similarly, if we take some more hydrocarbons like methane, CH4, which constitutes about 75% of natural gas, and if we burn this methane in presence of oxygen, it burns, these hydrocarbons burn to give carbon dioxide, water, and again, energy is released in the form of heat and light. We can take one more example of C4H10, that is butane. Butane constitutes of it constitutes 95% of LPG is butane. Butane is the constituent of LPG gas, 95%. Ethane and propane being 5%. If this butane is burnt in oxygen, it again gives carbon dioxide, water, and again we have energy. Now if we take ethanol, C2H5OH, this is ethyl alcohol or simply ethanol. If we burn this ethanol, this ethyl alcohol, the result will be same as in case of other hydrocarbons. So in a nutshell, we see all these carbon compounds, all these hydrocarbons, these carbon compounds, they burn in oxygen. They undergo combustion. They combine with the molecular oxygen and result in the formation of carbon dioxide, water, and release large amount of energy. Because of this act, they release large amount of energy. These are also used for process of burning and are referred as simply fuels. Now, fuels are the substances which are burned to produce energy mostly in the form of heat and light. Likewise, we have two main fuels, which are coal and petroleum, and they are also referred as fossil fuels. Why so? Because this coal and petroleum, they are basically the dead remains of organisms, either plants and animals of prehistoric times, and now in these millions of years, due to the process of carbonization, that living, dead, decaying material converted into something which can be used as a fuel, so they are referred as fossil fuels. Fossil fuels. Now, this was about combustion and fuels. When we talk about fuels, we had seen that there are many fuels which may burn with flame, or there are many fuels which will not burn with flame. For example, if I am burning wood. Now, wood is a fuel which burns with flame. But if we talk about charcoal, charcoal burns without flame. Now, what is it that few fuels, they burn with flame, and there are certain fuels which burn without flame. See, when we talk about fuel, fuel can be a simple compound, or it can be a mixture of compounds. So it can be just one compound, or it can be a mixture of compounds. Well, if this fuel, if this compound, or any compound in the fuel is volatile, volatile means it's on heating, it forms vapors. If it is volatile, then it will burn with flame. So the fuel burning with flame must be having some volatile substance within it. Now, if this, like charcoal, it burns without flame, so it must be a non-volatile fuel. So, based on their nature, whether they are volatile or they are non-volatile, they will burn with flame and or without flame. Those which are having volatile substances within it, or those fuels which are itself volatile, they will burn with flame, and those which are like without this, they are non-volatile, they will burn without flame. So this was about the flame, burning of fuels with flame or without flame. Second thing is, there are many fuels which burn with clean flame, and there are fuels which can burn with a sooty flame. Tam sei minut seed, sizes. Tam is also met hem zerto tret zo. Ah, şamasa? Tim que zani söyle? Tim que zani söyle az? So fuels burning with flame and without flame. After that, we have the fuels which are like burning with sooty flame, and the fuels which burn with clean flame. Now, it again depends upon the nature of the fuel. If fuel is undergoes complete combustion, it burns properly in adequate supply of oxygen, resulting in its complete combustion. So what will happen, it will result in a clean, burning with a clean blue flame. And there are less chances that it will produce that soot. Now, if this fuel is having incomplete combustion, definitely the incomplete combustion will result in the formation of, there will be some unburnt carbon particles left behind, resulting in the development of soot, which sticks to the outer surface of these, undersurface of these utensils. You see the black mass. So that soot is formed because of that incomplete combustion of the fuel. And if the complete combustion of the fuel takes place, there is adequate supply of oxygen, and resulting in the complete combustion of the fuel, it will produce clean flame. If there is incomplete combustion due to the inadequate supply of oxygen, will result in the formation of soot, burning with a sooty flame. Now, the second property that we will be discussing about carbon compounds is oxidation. Oxidation simply means addition of oxygen. And here you can see this, I have written this oxygen, atom of oxygen within these brackets. It simply means nascent oxygen. And this nascent oxygen is not available in nature, but provided by some oxidizing agent during the course of reaction. For example, C2H5OH, this is ethanol, can be also written as CH3CH2OH. This is the second member of alcohol family, ethanol. If we treat this ethanol with alkaline KMNO4, potassium permanganate, or with acidified K2Cr2O7 potassium dichromate, we will see this ethanol will get oxidized to ethanoic acids. So what happened here is simply you can see there was just one oxygen in ethanol, and in this case of ethanoic acid you see there are two oxygens. So there is perhaps the addition of oxygen, and this oxygen came from where we had seen that there are these two, either alkaline KMNO4 potassium permanganate or acidified potassium dichromate. They supply with this nascent oxygen because both of them are strong oxidizing agents. So these strong oxidizing agents, what they do, they supply with this nascent oxygen. This nascent oxygen oxidizes ethanol to ethanoic acid, resulting in the oxidation. This was the oxidation concept of oxygen with reference to ethanol and ethanoic acid. So we are having these two properties. The earlier one was combustion. This is oxidation. The third property that we were supposed to discuss was about addition reaction. And the fourth one was substitution reaction. Well, these two had been already discussed in my earlier topic when we were discussing about the versatile nature of carbon. I discussed both these addition and substitution reactions there. So we are done with these properties of carbon compounds, and thanks for the day. In coming days we will be discussing about a few more topics related to carbon and its compounds. Thank you very much.